Welcome back to the deep dive. Today, we're tackling something maybe a bit unexpected. Welding inspection and testing.
Yeah, sounds dry maybe, but it's actually fascinating stuff.
It really is. We've got this incredibly detailed technical document, basically the rule book for making sure welds hold up.
And our job today really is to pull out the crucial bits for you.
Mm.
Cut through the jargon.
Exactly. Show you why these steps are so vital for, well, keeping things safe and working properly. We'll get into why you need certified welders, the surprising geometry inside a weld.
And how we can essentially see through steel to find problems. It's pretty cool, actually.
Okay, so let's kick off right at the start. The
Okay.
person doing the welding. This document makes it really clear you can't just grab anyone off the street for important welds.
No, absolutely not. Welder qualification is step one. It's fundamental. They need proof they can do the job right according to specific procedure.
Proof, like certificates and tests.
Exactly. And there's documentation. The inspector, they have a role here too. They check that the welder has the right qualifications for the specific weld being done.
So it's not just a general good welder badge.
Precisely. And the manufacturer, the company doing the work, they have to keep track of all this. They need sort of an up-to-date list of who's qualified for what. It's about traceability and responsibility.
All right, makes sense. So, okay, you've got your qualified welder. Now, before they even strike an arc, seems like there's a lot about getting the metal pieces ready, the joint itself.
Oh, definitely. Joint prep is huge. How the edges are cut, cleaned, aligned. It all has to be just right. And then there's this idea of nominal thickness.
Nominal thickness. Okay, that sounds like it could be tricky. It's not just how thick the metal plate is.
Not always, no. It depends on the type of weld. So for a fillet weld, think of like joining two plates at a right angle.
Yeah, like a T-joint or a corner.
Right. For that, the nominal thickness is the throat dimension. It's the shortest distance from the root, the corner, out to the face of the weld. Okay. Then for groove welds, where you've maybe beveled the edges to make a V shape.
Right, to fill it in.
Exactly. The nominal thickness there is the depth of that groove plus any reinforcement, extra weld metal deliberately added on top.
Mm-hmm.
And if it's a single-sided groove weld, just one piece is beveled, it's basically the groove depth or the allowed reinforcement, whichever one's bigger. These details matter because they tie directly into the weld's strength calculation.
I see. So the definition changes to match the geometry. And are there rules about how thick the weld itself needs to be relative to the metal it's joining?
Oh, yes. For fillet welds especially, the required thickness is often linked directly to the thickness of the parts being joined. You need enough weld, but not too much.
A balance.
A balance, yeah. And if you're joining pieces of, say, different thicknesses, there are specific rules about the transition. You need a gentle slope on the weld surface between the thicker and thinner parts to avoid stress points.
Like a little ramp. Avoids a sharp corner where things could crack.
Precisely. And the document also calls out specific requirements for things like nozzles on pressure vessels or where tubes connect into a tube sheet in a heat exchanger. Those are critical spots.
High stress areas, I imagine.
Very often, yes. So the dimensions and the weld profile are really carefully controlled there.
Okay, so qualified welder, perfect joint prep. Now, the actual welding, it has to follow a plan, right? Not just whatever the welder feels like doing.
Absolutely not. Everything has to be done according to a qualified welding procedure specification,
Yeah.
a WPS.
Okay.
Think of the WPS as the tested and approved recipe for that specific weld. It details everything: the welding process, the filler wire, the voltage, the amperage, travel speed, everything.
And the welder qualification we talked about earlier,
Yeah.
that links back to this WPS.
Directly. Being a qualified welder means you've proven you can follow a specific WPS and produce a good weld consistently. You've passed the test for that recipe.
Got it. Okay, weld's done. Now what? How do we check it? First glance.
Yep. First up is a surface examination. Basically, a good visual inspection by someone trained. They're looking for obvious problems on the outside, cracks, places where the weld didn't fuse properly, big pores, undercut, like a little groove melted into the base metal right at the edge of the weld. It can be a weak spot. So yeah, catching the surface flaws first.
And then we need to look inside, right? That's where things like radiography come in. Like an X-ray for welds.
Exactly. Radiographic examination, or RT, uses X-rays or gamma rays to create an image of the weld's internal structure. Lets you see things like porosity, slag inclusions, lack of fusion, stuff hidden inside.
And it's used for critical welds, where internal flaws would be really bad news.
That's generally the idea, yes. The spec tells you when it's mandatory.
And reading these X-ray images,
Yeah.
It's not for amateurs, I guess.
Definitely not. You need qualified, certified personnel to interpret the radiographs. They're trained to recognize the patterns, the shadows that indicate different types of flaws and judge how serious they are. It's a skilled job.
What makes a good radiographic image? How do they know it's clear enough?
Well, there are standards for the image quality itself. You need to be able to see a certain level of detail. Often they include a little device called an image quality indicator, an IQI, in the shot.
Like a test pattern?
Sorta, yeah. If you can see the required features on the IQI in the image, you know your technique was sensitive enough. Then, for evaluating the weld itself, say a butt weld joining two plates,
Uh-huh.
they look at the length of any imperfections, how well the plates are aligned, things like that.
Are some types of internal flaws an automatic rejection?
Generally, yes. Things identified as cracks or lack of fusion between the weld and the base metal, or if the weld hasn't penetrated all the way through the joint, those are usually deal breakers.
Okay. What about things like little bubbles or spicks inside?
Rounded indications like porosity or small inclusions, those are typically evaluated based on their size, how many there are clustered together, and their distribution over a certain length of weld. There are charts and rules for it.
Complicated.
It can be. And an interesting point, if you're radiographing a butt weld between two different thicknesses, you usually apply the acceptance rules based on the thinner piece.
Because that's likely the weaker point.
That's generally the reasoning, yes.
Now, radiography sounds pretty intensive. The document also mentions spot examination. Is that like random checks?
Pretty much, yeah. Spot radiography means you only examine certain locations, not the whole weld, maybe one shot every few feet, or a certain percentage of the total length.
Why do that instead of the full examination?
It can be a less costly approach, often permitted if the welder or procedure has a good track record. It provides some level of quality control without the full expense of 100% RT.
But what if that one spot they check happens to be bad?
Well, that's the catch. If a spot examination reveals unacceptable flaws, it usually triggers more extensive inspection. You might have to go back and examine the entire weld, or maybe even more welds made by that operator or procedure.
So finding one bad spot can lead to a much bigger investigation.
Exactly. It encourages consistent quality. The specs usually state a minimum amount, like maybe 15% coverage for spot checks, and the inspector typically picks the locations.
And the acceptance criteria are the same as for full RT.
Generally, yes. A flaw is a flaw, whether you found it in a spot check or a full examination.
Okay. Besides radiation, what else? You mentioned ultrasonics earlier.
Right, ultrasonic examination, or UT, another key non-destructive method. This one uses high-frequency sound waves.
Sound waves. How does that work?
You send pulses of sound into the weld. If the sound hits a discontinuity, a crack, a void, an inclusion, some of that sound energy bounces back, like an echo.
Like sonar or how bats see.
Exactly like that. The instrument measures the time it takes for the echo to return and its strength, which helps the operator figure out where the flaw is, how big it is, and sometimes even what type it is.
Clever.
Yeah.
And again, you need trained operators for this.
Oh, absolutely. UT requires significant skill and training. Operators need to be qualified, follow specific written procedures for scanning, calibrating their equipment properly, and interpreting the signals. Acceptance standards are usually detailed in codes referenced by the main specification.
Okay. The document also gives a quick mention to magnetic particle and liquid penetrant testing. What are those about?
Right, those are primarily for detecting surface or very near surface flaws. Magnetic particle testing, or MT, works on ferromagnetic materials, basically iron and steel.
Things a magnet sticks to.
Yep. You magnetize the part, then apply fine iron particles. If there's a surface crack, it disrupts the magnetic field, and the particles gather there, making the crack visible.
Okay. And liquid penetrant.
Liquid penetrant testing, PT, finds flaws open to the surface on almost any non-porous material. You apply a brightly colored or fluorescent liquid dye that seeps into cracks.
Soaks in.
Exactly. Then you clean the excess dye off the surface and apply a developer. The developer acts like a blotter, drawing the dye back out of the crack, creating a visible indication.
So MT for magnetic stuff, PT for surface breaking flaws on anything else.
That's a good summary. And like the others, they have specific procedures and acceptance criteria defined elsewhere, usually in referenced standards.
Wow, okay. That's quite a toolbox of techniques. Finally, there's a general section on inspection and tests overall. What's the big message there?
It really just reinforces that all the steps, materials, fabrication, examination, testing have to meet the requirements laid out. It's about total compliance, and it emphasizes the inspector's role.
The quality control person.
Right. They need access to the work at all stages. They verify documents, witness tests. They're the independent check ensuring everything is done according to the book, the specification.
It's genuinely striking the level of, well, rigor involved. So many checks and balances just to make sure a weld is right. It's definitely not a simple process.
Not at all. From checking the welder's ticket before they start to prepping the joint just so, following the recipe, and then scrutinizing the finished weld inside and out, it's all about ensuring safety and reliability.
It really makes you wonder, doesn't it? When you think about this level of detail for welding, what other everyday things that seem simple, have these hidden layers of quality control, ensuring they work and don't fail?
That's a great point. It really highlights the unseen engineering and effort that goes into making sure the bridges we drive over, the planes we fly in, the power plants that give us electricity actually function safely day after day. A lot goes on behind the scenes.